Okay, so no one has joined till now. Let me wait for a few minutes. Then we can start. We can start now.
Okay.
Okay. Screen is visible.
Yes.
Okay. So last day we are discussing a problem, and due to some uh, error in calculating units, we stopped. So let us discuss that. Probably we are correct. Okay, there was nothing wrong because later I checked also the same answer I was getting. Probably the answer given in the book that may be wrong, or maybe some uh, error, some wrong data was provided. That also happened, but we'll proceed considering the provided data. Okay, then we'll see whether answer matched or not. But I checked, but still. You also
The process will be same.
process was same. Process was correct. I thought due to changing the unit conversion, there was some mistake. But later I checked, I did not found them. Okay, so it was probably correct. So that's why I don't know. Maybe the given provided data was there was some uh, mistake in error in units. That may also happen, but I don't know. But the answer is not matching. From where I took this question in that book, also the procedure was not there. The answer was given. Uh, the procedure will be same. There is no doubt. But I don't know. Let us do it again. You also do it. Okay, simultaneously. Then we will check whether the same result is coming or not. If our result matches, then whether it match with
Okay.
provided data or not, provided answer or not. Yeah. After that, the fugacity part. Okay. Fugacity we will discuss. Okay. The question is, at what pressure? At what pressure ice will melt at -1 degree centigrade, assuming that delta HF is independent of pressure, and the delta HF is given. Probably this value may not be correct. I don't know because the answer is not matching. That's why I'm saying. In generally, I did not check the delta H F, but other data I also checked. Let's see. When the delta H F is given, that is 60095 kilojoule per mole. Okay, and the given densities are density of water is gram per cc, and density of ice that is also provided to us 0.91. This was the question. Let me once check the delta Hf for water, whether that data is correct or not. Heat of this data is not correct. Okay, let me check. It is given this data fusion per mole. Let me do it. No, no, it's correct. 6.01 kilojoule. Okay, so every data is correct. चलो देखते क्या होता है. Okay, so now
Density of water and ice.
that is correct also. That I have checked. Density, you can also think that water we know. Water is around 1.
Yes.
That is already given. And
Ice is less than 1.
volume of ice is generally greater than volume of
Greater
water.
than volume of
Okay, so density should be less than.
less than water.
That is also giving. So it's correct. It's correct. Okay, I don't know. Okay, so now it is given at they want to calculate, they ask to calculate the pressure. Which pressure? Ice will melt at -1 degree. In general, at 1 atm pressure, it melts at 0 degree centigrade, right?
0 degree.
And they have asked the pressure, let's say at P atm, any, I don't know, that pressure, it melts at -1 degree centigrade. They ask. Okay. So for solving this equation, we'll generally, we will obviously use the Clapeyron equation.
dp by dt equals to del H by T del V.
Del P by del T, or dp by dt, whatever you want to write here, only one derivative. So dp dt is equal to del H by
T delta V.
T delta V. Now, this is a melting process. So solid to liquid conversion is there. Okay. So solid to liquid conversion means the delta V will be
Positive.
liquid. No. How you can say that delta V will be positive?
Liquid minus solid.
So that can vary. You don't know whether the VL is greater than VS or not. Okay. For
Yes.
ice, V liquid is smaller than V solid, I think. Yes. So it is negative
Yes.
for
So there
ice.
is negative.
Hmm. So it is not obvious that always delta V will be positive. Yes, except this liquid to solid transition. But if it is solid to gas or liquid to gas transition, then you can obviously say, then obviously it will be positive. Okay, so now if you solve it, so it will be delta H fusion delta V, and you can write dt by P. After integrating, it will be P2 minus P1, that will be delta H fusion delta V. This is the delta V, and this ln, this will be ln T2 by T1. Okay, if you put it, P1 is 1 atm, then P2 will be 1 plus
1 plus
delta HF VL minus VS. This will provided the unit. Okay, this will provided the unit because this part is unitless totally. This is the logarithm. So now then it will be ln 272 by 273. So first let us do this part totally, and this is totally ATM. This is in ATM. This is unitless. So we want to calculate this also in ATM. That we'll do later. So it will be 1 plus, it will be minus, because ln 272 divided by 273, this is okay, minus 3.669 into 10 to the power minus 3 times this factor. Let's say this factor is beta, or any factor gamma. So this gamma we will calculate in ATM. We want to calculate this gamma. Gamma is, this is a pressure. Okay, this we want to calculate in ATM. Our task is this. This headphone is irritating totally. Change it. I don't know. This gamma is defined as, okay. So delta HF we know. Okay,
yes.
delta HF totally given, but we have to calculate this delta V part. So now delta V, eventually it is VL minus VS. So you can write it. We know that density is mass by
Mass
volume.
by volume.
So it will be mass divided by, or you can write it, volume is mass by density. So it is d liquid minus d solid. 1 by d liquid, this is given 9998. Okay, and this will be minus 0.9970 gram per cc. Okay. Gram inverse cc. So this will be the unit. Is it clear?
Yes.
So now if you calculate it, so what will be the value? Let me do it. 1 by, it is giving a minus result. And what is the M? M is 18 gram per mole. This is, for water.
Yes.
So it will be 18 and gram per mole. So gram will be cancelled out. So it will be the unit. This is the unit of volume. Yes, correct. Molar volume. Okay, is it correct? Totally, I think it's correct.
Yes. Minus 1.6256.
Perfect. Yes, it's matching. So this is our delta V. Okay, delta V we obtained totally. Now the gamma. So gamma will be, as it was mentioned, and this delta HF. This delta HF is 6.0095. 6.0095 kilojoule per mole, right? So it is 10 to the power 3 joule per mole. And the denominator is totally minus, obviously there is a minus sign, 1.6256 centimeter cube, and mole inverse we cancel. Okay, so this is the total unit, and joule is Newton meter.
Yes.
So just we have to convert the centimeter cube to meter cube.
Meter cube 10 to the power minus 3 minus
10 to
6.
the power minus 6 meter cube. So it is the unit. So do it.
It is
What is
in
the answer?
Pascal.
Newton per meter square is Pascal. Okay.
Minus 3.69678 into 10 to the power 9.
Let me also do. Yes, minus 3.6967 into
678.
10 to the power 9. Okay, Pascal. So just we are carrying what are we getting. So now we have to convert this Pascal to atmosphere.
ATM.
Huh. And if you don't remember, then we can do it using the R. Correct? So R is
Yes.
0.0082
8 to liter atmosphere. Mole to the power minus 1 Kelvin to the power 9.
liter ATM. Mole inverse Kelvin inverse is there, so we are not bother about that. And it is 8 point
C14 joule.
joule, only joule. Okay. So liter ATM and joule there is. Uh, and we want to have the relation between liter ATM, ATM and this is actually Newton meter. Okay.
Yes.
Liter. Liter is 1 decimeter cube. Okay. And 1 decimeter cube means 10 to the power minus 3 meter cube.
Meter cube.
So this is the answer. So this is the Pascal. Okay. So if you do it, so it is
101.4 into 10 to the power 3.
so 1.0139 in 10 to the power 5. So this is the definition
Yes.
we already know basically. So this Pascal is this ATM. So 1.0139 to 10 to the power 5 Pascal is equals to 1 ATM. But we have how many Pascal? This, right? Mm,
Yes.
okay, it is in minus. So ठीक है. So it is 3.6967. 3 point to 10 to the power 9, I guess, right?
Yes.
So do it. 3.464.
3.646 in 10 to the power 14. Sorry, 4.
Okay. So this is our gamma. Gamma is there is a minus sign. This is our gamma. So now if we know the gamma, then we can do it. We have the form. This is the form, right?
Yes.
So this is our P2 in ATM. I think this is correct. We don't know what mistake we had done yesterday, last class. So it will be now plus. So do it. So 13.377
13.377 into 10 to the 10.
into 10. This ATM. That we have to accept actually. This is not very bad number even. So it is eventually this. This ATM. 133.77
Why?
ATM. Why means?
So many pressure is needed for minus 1 degree Celsius. Is not absurd.
I don't know. This is the coming and all data are correct. So how you can say this is absurd?
It should 10 to 15 atm. That means low pressure, much relatively than that, because we have to melt it at minus 1 degree Celsius instead of 0 degree Celsius.
Hmm. No, you are saying correct. I also expecting if it is 10 to the power 1, right? And if it is 10 to the power minus 1, then it will be very good, right? But that is not happening.
Yes.
That is not happening. That I said now. We are what we can do. We are getting this, and I can check the relation between the atmosphere and Pascal as well. That is also correct. Let me also check again once. It's correct. It's correct.
Which one?
Atmosphere and Pascal.
I remember it. It's correct.
It's correct.
1.014 into 10 to the power 5.
10 and this is it. There, no mistake is there, na? Mistake. This is also correct. This delta H is correct. Delta V is also correct. AM is correct.
What is the experimental value?
That I don't know. That I don't know. This
Can
maybe.
I find it from Google?
You can check. You can check if you find it. But mathematically, I don't find any uh, error. You check it if you. I also. It's straightforward. These 10 to the power 3 coming from kilojoule and 10 to the minus 6 coming from meter centimeter conversion. So it should be
What is our
in the
answer?
difference.
Experimental value is 138 atm.
It's correct. It's correct.
Yes.
Correct. We are wondering about this huge pressure, right? That is
Yes.
correct.
Okay. So it is the truth.
Fact.
Yes.
Okay. Okay. So now, hmm, this type of question I did once, but let us do it. Then we will start the fugacity. One more question left. Yes, only one. Better you should try it because last time you had doubts, I think.
Yes.
It's not from thermochemistry. It is like that heat transfer. Okay, let me write it. 150-gram mass of copper at a temperature of 393 Kelvin is placed in a contact with use up value of okay. One question we discussed this type of question, right? That's why I thought we
Yes.
should discuss it as well. So try it, think it, and solve it. Should I do or you can try? You'll want to try.
I am trying it.
Okay, let me. Okay, try. Then So let me start it. Eventually you also try it, so then we'll check the answer. Okay, so
Okay.
a 50 gram mass of copper, anything here copper, at temperature of 393 Kelvin is placed with a contact of 100 gram mass of copper at 303 Kelvin. Zero law of thermodynamics we have to use totally in a thermally insulated container. So let me draw a thermally insulated container, and there is two copper. One has mass of 50 gram, another one is mass of, it's not over, 100 gram. Okay, so now this is 50, this is 100. Hmm. After some time it will reach to some equilibrium. So this is easy because here no phase transition will happen. The previous problem we discussed, there the solid to liquid transition was happening now. So that's why it
Yes.
was quite non-trivial, but this is very much straightforward. Here both copper will be copper, means solid will be solid, liquid will be. So it is solid eventually. So let's say it goes to any T temperature. Then we have to calculate Q and delta S total. Okay. What will be Q? Formula of Q is M. Do you remember?
M. Yes, delta T.
M S delta T. S is specific heat. Let's say this is A, this is B. Okay. So this is the value, and eventually delta T at delta T should you should consider the mod always. This is the best sign. So now what you can then you can say here, obviously QA equals to QB. So you can write. So you see mass is different. So this will be mass A, mass B. I have to write it, and S will be same because both are copper. Both are copper. Yes, copper, copper. I think S is not
Yes, S is same.
here. Here. So it will be MA delta TA. What is delta TA? That you can see here. You have to take the mod of delta TA. It is eventually T minus 50. 50 means 273 plus 50. Okay, so it is
323.
323. It should be equals to MB of, sorry,
373.
373, or it is at 100 degree, right? Yes, 373. 1 minute. No, what are we doing? 50 gram is weight. Sorry. 393
Oh,
and
393 and 303.
393 and 303. So 393, here it will be 393 and it will be 303. Okay, and MA is 50, MB is 100. So you can write it as this. Okay, so eventually T should be lies in between 303 and 393.
Yes.
Okay, so what we can write it, it is eventually 393 minus T, and it is right, T minus 303. So 2T, sorry, 3T equals to 393 plus 606. Oh, 999. So T is eventually 333 Kelvin. So T we have obtained. So now easily we can calculate the Q. Q is any, you can take QA or QB, anything that will be the same. Q equals to, so let's say MA S and delta TA. So it will be MA is 50 gram. Now S will be required, which is given as, let me write the unit given,
0.4184.
4184 with the unit of joule, gram inverse, Kelvin inverse, and delta TA is 333, sorry, 393, I think 393 minus 333. Yes, Kelvin. So it will be straightforward because all our unit correct unit is already considered. 333, so it is 60 into 50 into 0.4184. So it is 1255.2 joule or 1.2552 kilojoule. So this is our Q. Now you have to calculate the S, entropy. This part is new, but you know how to calculate the entropy.
Q reversible by T.
It's okay, but there was formula na NCV LNT2 by T1 NPLN.
NCVL T2 by T1 plus ln.
This formula is there, but here's only temperature is changing, but it is a constant volume process or it's a constant pressure process, that you have to understand. Okay.
Isolated it is.
It's isolated, but you can use the both there are both formula na? Let's say, let me, if I want to write N CVLN T2 by T1
Plus NR
minus
ln V2 by V1.
plus NVLN. Okay, I just V2 by V1, or you can write it.
NCP ln T2 by T1 minus NR ln P2 by P1.
So which formula should you use? CP or
This
CP?
pressure is this pressure is isobaric process because it is in atmospheric pressure.
Hmm. So will be 0. Okay.
Yes.
So we should use this formula. So we can write it. Actually, these are M. So N PM ln T2 by T1 because this is 0. No, this is 1. This part is 1.
ln
So what will
ln1
be
it is
0?
0.
So what is the CP?
We have to calculate it.
Calculate it. Calculate the CP. How you can calculate CP?
0.4184. It is given the specific heat.
But there is something, I think. This is, see, this is NCP. CPM means this is molar CP. Molar you have to consider.
Okay.
Okay. So that means there you see this value is given na. So which value is given to us? 0.4184 joule per gram inverse per Kelvin inverse. So this is per gram, but we need per mole. This you understand?
Yes.
Okay, because this is CPM per mole, and this value is per gram. So how you can convert it? You have to convert it gram to mole. And for copper,
By
63
dividing
gram,
with mole number.
63 gram equals to 1 mole.
1
Just
mole.
you multiply it with 63, then you can have this. Okay, so this is, and what will be the N? So eventually
One
this
mole.
no, this will not be same because S you have to calculate separately SA and SB because N is not same for both
Yes, 50 gram and 100 gram.
50 gram and 100 gram. So that will be the difference. So it is 50 divided by 63 into 63 into 0.414. Do you understand it?
Yes, that means
And
it's mass into Cp.
yes, obviously. In general, you can do it. It is CPNA. So Na means mass by that capital M, and it is M into small s.
Cp.
Small s.
Okay.
From there. So it is ln T2 by T1. T2 you have already calculated 3, 3, 3. Final temperature. And the initial temperature for A was TA, so it should be T by TA. And TA was 393.
393
So calculate it. So what will be the answer?
minus 3.4657.
Let me also do. Yes. 57. And what will be the unit? This is unitless, this is this, and this is our mole.
Joule per Kelvin. Joule per mole Kelvin.
This is no, 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 no. Here the gram will be cancelled out. It will be just joule per Kelvin.
But entropy is intensive.
Entropy is,
So sorry, it is dependent on the quantity.
huh? So it is depending, na?
There was a question and my answer was wrong because of this molar thing.
No, I don't
The unit
get.
the unit was in molar, but I selected the unit that was not in molar. The actual
Okay.
answer was joule per Kelvin. So what is this? Please explain it. Should we use molar or not?
Molar entropy, or what are you saying?
Yes, molar. That means the unit of the entropy. What is the unit of entropy?
Joule per Kelvin.
But in answer there was joule per Kelvin mole inverse.
That is molar entropy. It
Yes,
is for
but after
mole.
calculating, I was getting joule per Kelvin. Mole was cancelling out, but there then also it was in mole.
No, no, no. That should not be because original definition of entropy, what is entropy? dq per by t,
dq
right?
reversible by t.
So it is joule per Kelvin directly. No mole is there.
Yes,
If you are calculating per mole, then it is molar. There is no ambiguity. So similarly, you can calculate the SB. SB will be MB. This is, oh, sorry, NB CPM ln T by TB. So NB is again, it will be 100, obviously 100, and you can directly calculate it 4184, but this will be now 333 divided by
303,
303. Yes. So calculate it, it will be
3.95.
okay. We have already calculated. Okay.
Yes,
Hence, total entropy change that will be del SA plus del SB. So it is 3 point minus 3.466 joule per Kelvin plus 3.950 joule per Kelvin. So it is 0.54.
0.484. Yes,
Okay, so delta S is positive. That means it's a spontaneous process, and that we have
spontaneous.
already discussed. So this is the total entropy change. Okay, so is it clear?
Yes,
Now we can discuss the fugacity part. See here yet? Yes, sir. This is very confusing. Okay, see. Okay.
Yes.
So, for ideal gas, this is, I'm just explaining the theory behind this, and then we'll solve a few questions. And then if time permits, then one or two question from thermochemistry we can discuss. Okay, so this is uh, what does it call basically? This is just effective pressure.
Its unit is same as pressure.
Pressure. Uh, Pressure of a real gas. So how you can think like this? Just the activity and concentration. If you remember, there is a relation between
Yes.
activity equals to gamma c. This was
Activity
concentration.
coefficient into concentration.
Uh, this is concentration. This is activity coefficient, and this is our activity. Okay. So because for very dilute solution, this concentration and activity become the same. Correct?
Yes.
So for the real solution, you can see, then you have to consider the activity coefficient. Then it will give us activity. So here also similarly, for ideal gas, PV equals to nRT, but for real gas, P will not be there. You have to consider the fugacity. Fugacity is the real pressure. You can think like that. Okay. So similarly, what you can write will full same hai. Just you have to consider. We can write it. This idea is also came from there. Fugacity is phi times P. Here, this is our pressure. This is our fugacity, and this is fugacity coefficient. This is the active pressure. You can think like that. Effective pressure or active pressure. Okay. So if the gas was real, then the pressure will be P. But as the gas is not the real, if the gas is ideal, then pressure should be the P. But if the gas is real, all gases are real gases, then pressure will be F. That will be 5 times P. Similar to the activity concept. Is it clear?
Yes.
And this fugacity coefficient is totally unitless because fugacity and pressure both has the same unit.
Same
Okay.
unit.
So similarly from here you can say that for the very low uh, for very low density of gas, if you consider, then obviously this F equals to, or even closely goes to pressure. That means phi equals to 1.
At infinite dilution.
Hmm. If the density of any gas is very small, then
Why we need this fugacity coefficient?
because you have to deal with the real gas, you can't directly write the pressure.
Okay.
That's why you have to consider.
Which gas has more pressure, real gas or ideal gas?
That will depend between there is attraction present or what is the main difference in ideal gas. If you remember, we considered that
There is no interaction.
no interaction between the molecules, but actually there is interaction. So which kind of interaction is that? That will dictate the fugacity will be, that means phi will be 1 greater than 1 or less than 1. That's the case.
High can be negative also, or only
हाँ,
positive.
negative कैसे हो सकता है? How that phi can be negative?
It is between 0 to 1.
Pressure can't be negative. So
Yes.
any pressure can't be negative. Fugacity is also pressure. Okay.
Okay.
So now let us calculate the activity coefficient. How you can calculate the activity coefficient? So let me start with this. This is correct. Or you can say
Yes.
for a constant temperature process.
Yes.
D is equal to VdP. Okay. And for 1 mole, you can write it. Okay. D is equal to d mu for 1 mole. So it will be d mu equals to VdP.
Molar volume, basically.
If you want to write Vm, then you can. No problem. This is molar volume.
Okay.
So now what we can do from here, if it is an ideal gas, but in general, I will not write it. There is a reason between because we'll have to put another coefficient in subscript or superscript. That's why I'm not writing. But still, okay, this is now if it is an ideal gas, let's say for ideal gas. This is general equation. This is valid for ideal gas, non-ideal gas both. Okay, because as long as we are not using the ideal gas equation, uh, that means the equation is general. Thermodynamics equation can be applied for any case, any situation. Okay, this is not for even gas. This is for the liquid, solid, for everything. Okay, this is general equation. But let us considering an ideal gas. Okay, so for ideal gas, it will be del mu VdP, but let me write it as V ideal. Okay, and if we integrate it from P1 to P2, mu1 to mu2, then we will get delta mu equals to RT, because you know V ideal is eventually RT by P.
Yes. dp by p ln p2 by p1.
So this is the delta mu. This relation we already know.
Yes.
So you can write delta mu ideal okay. But if it is not an ideal gas, then obviously this should be changed, because you know for real gas we have to replace pressure by fugacity.
Yes.
So you can think like that for real gas it is FB equals to nRT, like this. Okay,
Yes.
for real gas. And it's true even. It's true. For Van der Waals gas, what we write?
p plus a by v bar square v minus v bar equal to RT.
V is not, correction is V is not important. So we are considering only the correction in P. So that's, you see, for Van der Waals gas, F is eventually P plus A by V square. So if you take the P out, then it is 1 plus A by PV square. This is the phi activity coefficient, like this. Okay.
Yes.
So for real gas, you can write it as delta mu real, it will be RT ln F2 by F1.
Yes.
Is it clear? It's direct. Phi will be the same because gas is same. Okay.
Phi is same for the same gas.
Phi totally depends on the characteristics of gas. So how you can write it? Let
It
me.
does not depend on the volume of the gas.
Mhm. PV equals to nRT, correct? And what is P?
Yes.
F by phi.
nRT by V or nRT by phi.
Hmm. nRT phi. So phi nRT. This is the relation. So if you put it, then you can get it. Phi will be cancelled out. Phi is same. Should I do or it is understandable?
Yes, it is understandable.
Okay. So now, so what is the change between this real value and this ideal value that we can calculate? What is the change? Change is RT ln f2 by f1 minus ln p2 by p1. This is the change. And what is this? V real minus V ideal into dp. If you remember, this we had only done
Yes,
from here. Okay. This is the in general definition. It was changing from P1 to P2. Now, if let's say we are changing P2 is P, but P1 is tends to 0. Okay. If we want to calculate, then what will happen? Then F1, this we know F1 will be P1 at very low pressure is very low. Pressure is very low means density is very low. Okay.
yes,
How you can write it? Because P for ideal gas in general. So it is eventually PV equals to nRT and it is N by V. N by V means N by V means N is actually M by capital N. So Pn equals to dRT. Correct? P N not N, capital M equals to dRT. This you know?
yes,
So it is directly proportional to density. So that's why low pressure means very low density. That's why you can write it F1 equals to P1. But in case of F2, you have to consider that phi p. Obviously, that you have to consider. If you use it, so then the above equation can be written as P1 is 0 to P2. So V real minus V ideal dP. That will be RT ln F2 is phi P2. Okay. You can write it RT ln phi. Is this clear?
yes,
Great. If you remember, there was a Z. Z was V real.
PV by RT, V real by V ideal.
Huh, that is called compressibility factor.
Yes,
What you are saying that is also correct because PV equals to nRT. This is for ideal, but for real, what will be the case? Then Z will be V real by V ideal. V ideal is nRT by P, so PV equals to nRT. PV real by nRT. You can write it as well. That you are saying, I
yes,
think.
yes,
So then it will be 0 to P V real minus V ideal. Okay, so V real can be write down as Z V ideal. So it is V ideal to take common Z minus 1 dp. Okay,
Yes.
and you see P2 was considered as P. So it is P, dummy variable. So it is just now V ideal is constant. Z is not Z can depend on pressure obviously, but V ideal you can replace it. Okay, how you can replace this V ideal?
NRT by
NRT
P.
by P. Yes. So it is, but everything was for 1 mole from the
RT
beginning.
by P.
RT by P. So RT will be cancelled out. So it will be just 1 by P. Okay.
Yes.
So phi is, this is the fugacity coefficient, is e to the power this. This relation is important.
This is the main formula.
Hmm. This is the formula for the activity coefficient, sorry, fugacity coefficient. So for one particular gas, this if you calculate the phi, then obviously you can calculate the fugacity for any pressure. Okay. So these things we have to just calculate. And this is a totally generalized formula. And you see the phi will depend. Phi will depend on a particular gas. That's okay. Except that for a particular gas also, this phi will change for the what range of pressure you are considering. See,
Yes.
and this is evident because already you have considered phi equals to 1 for very low pressure. This already you have considered. So phi should be dependent on the pressure as
On
well.
changing the pressure, the interaction is changing.
Yes, for the phi is
Yes.
so this already depend on this phi should be a function of pressure. Phi is not independent of pressure. So eventually this fugacity and pressure is not a linear relation between fugacity and pressure. If phi is independent of pressure, then you can say this is a linear relationship between fugacity and pressure.
Yes.
But phi is also dependent of a pressure, so this is eventually a non-linear relationship, and that should be non-linear relation. Okay. So from here you can write it. Let me write it explicit. Okay. Now we can simplify it. So up to extremum. So we can think. So if you want to calculate phi with pressure, because it depends on pressure. So when P tends to 0, so phi is already 1, you know.
Yes.
And now the rest of the part, you can divide it two parts. One is this part, like this very low pressure region, this is. And obviously there would be another region where the pressure is very high. So this may be the very high pressure region. In between, you can't
Yes.
explicitly say the relation, but to extreme situation, you can discuss. So we'll discuss that to extreme situation. First is
Low pressure region.
low or moderate. Means up to this part maybe. Not totally. Because there is no clear boundary. Low or moderate pressure. So what will happen for low and moderate pressure? If you think, then you, now you have to consider
It
the
nearly equals to 1.
No. If you need to consider the difference between pressure and the fugacity. What was the basic difference?
What?
What was the basic difference between the fugacity and pressure? In case of ideal gas, there was no interaction.
Interaction.
So let's say you have a some beaker or something gas container, and there is 1 mole of some gas, any gas, let's say hydrogen gas or oxygen gas is there. So now, if you calculate according to the ideal gas equation, you will expect particular pressure. Okay, let's say for you are as you have 1 mole of gas. So let's say you are expecting 5 atmosphere pressure. Suppose. Okay, is this clear?
Yes.
Now, as but the gas is not the ideal gas. So obviously the pressure will not be 5 atmosphere. It may be greater than 5 atmosphere or less than 5 atmosphere.
Yes.
That we have to consider. So how it will depend? That will depends on the interaction of the molecule. Because in ideal gas, we consider that there is no interaction between the molecules. That's why the pressure is that pressure is the ideal pressure. What happens in low density or low pressure? If the pressure is very low, if say if it is very tends to zero, then obviously the density of the gas very low. Correct?
Yes.
If the density of gas is very low, then the attraction or the repulsion between the molecules that
That will be
between the
negligible.
that will be negligible. That means that is the ideal condition. That is the reason that ideal pressure was equals to the fugacity in that condition when pressure tends to zero. But now this is important. Now we are considering the low pressure or the moderate pressure. For for that case, obviously, the interaction will be important. Okay, that
Okay.
is that clear? But if now you think pressure is low, that means density is less. So density is less means the particle is not very close to each other. Okay, okay,
Particle means?
particle, molecules.
Okay. Okay. Sorry.
Molecules are not very close to each other. So
Yes.
if you remember, there was a Lennard Jones potential. These things, if you studied,
Yes.
okay.
Yes.
So this was kind of this, right? This is
Yes.
between two R, and this is the force ionic, not ionic, intermolecular force. So this was something like that. So you see, if the particles are very close to each other, then there is a repulsion. This part is repulsive part,
Yes.
and this part is attractive part. So we are considering this means this, let's say R0. That means we are now R is greater than R0. We are in that region. Is it clear?
Yes.
Okay. If attraction should be greater than F repulsion, because total force is attractive force. Okay.
Yes.
So now if attraction is more, that means the pressure will be the less. Get it?
Yes.
Okay. And this region is that tends to infinity. That is low pressure, very low pressure region. In that case, it will be same. But if the attraction is greater than repulsion, that means you can say the fugacity, this F is force. Okay, the fugacity will be less than the pressure. Okay,
For low pressure region.
for low pressure, low or moderate pressure. That
So the
as long
phi will be always less than 1.
I will be always less than one, as long as a R is less. Okay,
Yes.
You can think it, you can visualize it by using now. You can do it even explicitly. This is very irritating. Why this is happening several times? Okay, for Van der Waals gas, P, everything is for 1 mole. Okay, and we are totally now considering this low and moderate pressure. So there are two coefficient, A and B coefficient, and for this attractive part, obviously A will be greater than B, dominating part. If you remember, if there is
Yes.
attraction, then the major correction will be in the A part, not in the B part. So you can easily write it as P plus A by V square RT. Now I'm just doing it by math, considering an expression. So if this is the case, so this is okay. So this volume is real volume. This volume is not ideal.
Yes.
This everything is real. So this will be then Z plus A by RTV equals to 1. Or you can write it Z is less than 1. And if you remember, so the phi was ln phi was 0 to P Z minus 1 by P dP. So Z minus 1 is less than 0. So it will be now less than 0. That means phi will be less than 1. That already we have predicted conceptually.
Yes.
Okay. So this is the low or moderate pressure case, as long as this A is heavily greater than B, or you can say this R is greater or equals to R0. That part, as long as correct. Okay. So this definition already clear. At low or moderate pressure, force of attraction dominates. Therefore, the force by which a molecule hits the container that decreases, that's the pressure of the real gas, that is the fugacity, is less than the pressure or the expected ideal gas pressure. Okay.
Okay.
Now the second case. What is the second case? That is the high pressure. So you see, in this region, let me draw it like this. Pressure is eventually the negative. So it was 1, but for low or very moderate pressure, it will be less than 1, like this. I'm not drawing totally, that part I will see, uh, because we need this definition as well, that high pressure region.
But pressure cannot be negative.
Pressure is not negative, the phi is negative.
Okay, that means the pressure is negative. F equal to phi p.
Not negative, sorry. Oh, what I have writing? This is 1, 1. Okay,
Oh, less than 1.
less than 1, 1. That we have already discussed. Now, let me draw
Yes.
it here. Let me draw it here as it is. छेद नहीं करना चाहिए.
Ln phi is less than 0 and phi is less than 1.
But we need is one more. Let me draw it for 1. Let's say this is the 1. So this part, less than 1. Probably ये भी हो सकता है, कुछ भी हो सकता है. That we'll see what will happen at the high pressure region. Then we will draw the total curve. Okay. So phi is less than 1, not less than 0. I draw it wrong. Okay. Now we are interested in the high pressure region. So generally, already we have drawn this. This let me copy paste there as well. But this is the capital F. This F is the force.
It is not fugacity.
No, attractive and repulsive force I have drawn here
Lennard-Jones potential.
from Lennard-Jones potential. This F attracts and repulses. Na? This F is fugacity. Okay. So
Okay.
now we are at R that is less than R0. So if that is the case, then eventually you can say that the F repulsion is greater than attraction force. Repulsive force is greater than the attractive force.
Yes.
So that means the molecule will be moved faster, okay, and hit the walls more with the more force. That means the pressure will be more. As expect
Yes.
you, if it was an ideal gas, consider that it will be the more pressure. That means the fugacity will be greater than ideal gas pressure. That means phi should be greater than 1.
Greater than one.
And this can also be shown by using that ideal gas equation. Now here, obviously, B will be greater. So if you apply, then you can write P plus A. Let me write the original equation first.
A tends to 0.
A can be negligible here. So it's very high pressure, high temperature. Oh, sorry, high temperature, high pressure. So now it is B minus V by B equal to RT. So what you can write? PV by RT equals to RT by PV by RT. Okay, minus, sorry, equals to 1. Okay, so this is Z,
1 plus BP by RT.
1 plus PV by RT or BP by RT, whatever you want to write. This is Z. So Z minus 1 is this. So phi will be, or ln phi will be
1 by P dP.
so it will be P will be by RT. So RT will
But the formula was
be
dP.
okay.
Yes.
So it is clearly greater than 0.
Yes.
Or you can write it even. What will be the case? Uh, B is there. RT will
BP by
be
RT.
BP by RT. So eventually this should be P prime. Okay. Uh, we have to should use a dummy variable because P is variable and P is a particular pressure, that is confusing, right?
Yes.
Okay, but it is understandable. So phi is greater than 1. So this is our high pressure case. So now see, ln phi is this. So phi is obviously e to the power PV by RT. So this is an exponential behavior. An exponential
Yes.
behavior. So here it will be purely exponential. The behavior,
At high pressure region.
uh, it will be purely exponential like these things. And here it is this, so it can be this. You don't know. This part you know, this part you know, but in between you don't know. So, but you can understand it should be, it should not be like this. That is totally not scientific. But here, this lesson you don't know. If you calculate this lesson, let me try it. If you calculate some this lesson, then you will have some idea. Okay, the this part is clear, correct? The high pressure part is clear. It is
Yes.
it. Yes. So in general, what will be the nature of the gas that we can calculate? Nature of the fugacity. Okay. So let me do it.
Nature of the
Here,
fugacity means it is greater than one or less than one.
mhm, fugacity coefficient greater than or less than
Yes.
1. Okay. So here the equation was this. Let me add one page here.
Yes.
Z Z minus 1 is minus A by RTP. Okay.
Yes. Minus A by RT ln P.
Considering A is independent of pressure. Just ad hocly
Yes.
I'm doing. Okay.
Yes.
This will be the nature P to the power minus A by RT. Something like that. So now if you want to A by RT, here also you had B by RT, PB by RT, but here it is A by RT. If I've not done any mistake, let me check. No, there is a volume. You see, here is a volume also.
Yes.
So it will be A by RT V. A by RT V. Now it is correct, I think. Yes. And this volume is the real volume. This volume will depend on the pressure even. So you can't bring out from the integration Tp by Pv. Then again, V is there now. So how you can ignore that V? Because you want to differentiate with respect to P, but Pv is there. So V, this is the related V. This V. Again P will be
Real V.
real V. This real V is coming now. This real V is coming. So for real V, you can't write that Pv
We have
equals
to
to.
substitute the value of the V.
But it will be again lengthier then. We can do. We can do from here, but you don't know that exact expression of V because V square is there again. So it will be a loop.
Yes.
So better you have to do some approximation. Let me check.
If we consider volume is independent of pressure,
How you can do that? Then everything is useless. That you can't do.
At very high pressure?
No, no, no. It is not very high pressure. It is low or moderate pressure already. Okay, but so then leave it. But here it is clear that it will be obviously a exponential function because
Yes,
ln phi is there, so phi e to the power something. So eventually it will be an exponential function that can be predicted totally. Okay. So if this is an exponential function, then you can draw it. This should be an exponential curve totally. Then it will be like this. It should be. Okay. So like this. This will be the plot. Fugacity versus P. Is it clear?
yes,
But in between it may take the linear sometimes because you don't know the what happens in between. That you don't know. Maybe
but
for
it is
some
every time exponential.
no no no. You are seeing from that equation, right?
Yes,
But due to some approximation in between that may behave like linear. Okay. That nature may be hold.
complete linear.
No. What is the form of e to the power x?
1
1
plus x by 1 factorial plus x square by 2 factorial.
something. So if
Yes,
for any value this part is ignorable, let's say, then it will be completely linear.
yes, 1 plus x.
That can happen. I'm saying I'm not sure, but in general, exponential should be there. Exponential characteristics that can hold. That's why I've drawn like exponential, like these things. Okay.
If special case arise, then it will be linear.
It can be that, but that is not important. We are interested in the very low pressure, very high pressure. But here we can do a trick to calculate the fugacity of a gas in general. Okay. For fugacity, what we can write that P okay, you can write it.
Yes,
Just we are considering the volume effect of volume. Pressure we will consider by the fugacity coefficient. That's why I'm not.
A is negligible.
It's a ideal gas. Now, if you corrected the volume part, you have to add B. Okay. So
Yes,
it's not ideal, not real. So you can see the partial, part, partly, partly real gas. You can think like that. When you have the approximation of A or the pressure approximation, this is a volume approximation, this is a pressure approximation, then it will be real gas, right?
yes,
So this is the partly real gas. We have approximated the volume part, but the pressure part, this will be accounted by the fugacity. Instead of A or B coefficient, we can do
yes.
that. We will do. Okay. So it will be V molar because everything is molar. Now it is Z minus everything is real. So now, so that's why it is correct.
Yes.
So
Z minus 1 by P dP.
so it is Z minus PV by RT. So it is
B by RT.
Okay, so you see the
But
volume
it
part
is
is
0 to 1,
0 to, no, 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 no,
1.
it's P. How 0 to 1? It is P.
Okay.
So you see here the only volume part is corrected.
Yes.
Pressure part is not. How pressure part we can do? We have to consider fugacity. That is already
By the
given.
velocity.
So this is total pressure part is already corrected. Okay.
Yes.
So this is the form.
Which one is most accurate? A
This
or bifugacity?
no bifugacity you can think, because A is for van der Waals gas. That is not for true or for real gas. Because you know don't know the expression of F. For van der Waals gas, the form of F is uh, P times 1 plus A by PV square for van der Waals gas, but you don't
Yes.
know. So you see that's matching now. P is there, and this part is e to the power PV by RT, something like that.
Yes.
Okay, you can relate because there is a van der Waals equation, so this part can be related. Oh, so what I'm saying, just what is the this is a van der Waals equation, right?
Van der Waals is also a special case.
That is not real gas, that is the van der Waals gas, obviously.
Okay. And fugacity is for completely real gas.
Hmm. That's why there is no specific expression of fugacity, na?
Yes.
So if you take common, so this part is RT by V minus V. So you can write it RT by V minus V. Okay, that's
Okay.
okay. That's okay. That will be now miss, but it is in general. Okay, now we can discuss some example. So I think the fugacity is clear. It's enough. No more discussion is
Yes.
required to understand fugacity. Let me check if there anything left or not. Sometimes this fugacity coefficient is also written as gamma, small gamma. Okay, so don't be confused.
Small gamma.
Small gamma. Okay, so let me do questions.
What are the type of problems?
I'm doing. Right. Then I will discuss.
Okay.
Let me check any other question if you are speaking.
Which formula I should use?
You have to calculate that DG, right?
Yes.
Now you can do it. So DG का formula, what is the general relation of DG?
VDP minus SDT.
That's it. Use it. Let me also do it. Okay. So what is mentioned? What they asked, free energy change, and this is 1 mole of gas, which is 57 degree. Okay, 25 to 280, and fugacity is given. Oh, so it's easy, I think. Do it. DG equal to BDB minus SDT,
Yes.
because T is fixed at 57 degree. 57 degree means 330 Kelvin, I think. Yes.
DT is 0.
DT is 0. Constant pressure, isothermal process. PDP, sorry, PDP. That you have to integrate. Okay. Is this clear?
Yes.
Okay. So how you can do it? So it is,
V is energy by P.
so it will be, is this for 1 mole?
Yes.
1 mole. So it is RT ln P2 by P1. But
Yes.
here you have to consider the real gas. For D
F2
equals
by
to
F1.
RT ln
F2 by F1.
F2 by F1. Any disconnected. Given.
23 and 91.
The 91 by 23. It's nothing. It's very easy. RT 23 and RT is do it. 40 is the answer.
Three seven seven 3.47. So why the pressure value has been given?
Where? Final initial condition, how you can check now? This is the final, this this is the pressure. This is P1, this is F1, this is P2, this is F2. Then how would you know that which is F1, which is F2? Okay.
Okay.
And you see that both F1 and F2 is less than P1 and P2. That means it's low and moderate pressure. This is
Yes. I was confused about using the pressure or fugacity.
no. When they have said the fugacity is this, then you have to replace the fugacity.
That means it's a real gas.
Obviously, yes. Otherwise, uh, you can use the pressure part. You can check the difference even. Okay.
Please give
This.
another problem.
I will give to worry. This was easy question,
Yes.
and this is also easy. Change is written as like this. You have to see. You have to show that this change is spontaneous.
Irreversible process and it is
Hmm.
spontaneous.
But how can you show that this process is spontaneous?
Gibbs free energy change is negative.
Exactly. Do it. Eventually, this is not question of a fugacity. Sorry, it is written here, but this okay. Do it, then we'll do it. nothing to do here.
Okay, I have done it.
Hmm. What is the temperature? 273. P2 by P1.
1/2.
Pg equals to du, or sorry, dh
VD, DH minus TDS minus SDD.
minus dt.
DT is 0. PdV plus VdP.
Okay, to put it. And du is sorry, um du is
DH minus PdP minus VdP.
mm, first law.
DQ minus DW.
Because
ES plus PdV.
plus it should be minus pdv. Minus pdv. Okay,
Yes.
so it's correct. vdv minus sdt. Okay, okay. So dg, so delta g
RTLN P2 by P1. 1/2.
mhm. And what is the answer?
Minus 3146.5.
Joule.
Yes.
So this is negative eventually, so it's spontaneous. Okay. Mm, okay, now it is a fugacity question. The last question. Okay, I think it's doable.
Yes. Please wait.
Mhm.
What is the number of moles?
1 mole because it's Vm is given, no? Okay, let me do it, and I will give one more question for you that you will do home, okay, by your own. So first you have to, I don't know whether I can do it or not. Let me check. So first you have to calculate the Z, correct?
Yes.
Because you have to calculate the fugacity. When you know the fugacity is nothing but
Phi
phi you
p
know. In this you have to calculate
e to the power 0 to 1 z minus 1 by
0
p
to
dp.
1, 0 to p.
Sorry, 0 to p.
Minus 1 by p you need. So Z you need. So Z we have to calculate for Van der Waals gas. That's our primary task. If you
Yes,
get
that I have
then it will
calculated.
be this one. So that how you can calculate because you know the equation.
Yes,
Z is
pp by rt.
okay. So how you can write it? Mm,
At first multiply, then divide by rt.
let me do it.
I am also getting the same.
Okay. So if you take common p by rt, but here will be rt, right?
Yes, v square rt.
So this you already know. So, yes. What is pressure? Okay, you can write it. Is it clear? Okay, from here, pressure, you can write it. Hello? Probably is disconnected. Okay, sorry. Hmm. So you can write it P like this.
Yes.
Hmm. So if you put it, it is, then it is, I don't know in which direction it's going. Times Vm square. So Vm square will goes away. It will be just minus A and this. Hmm. So, but it's okay. You can do. We can deal with this equation. This equation, right? Hmm.
Yes.
Hmm. In general, it is written as A by RT. Okay, you can show it
Okay.
due to some approximation. We can show it. This is actually PVM squared. But timing, if you consider this, whether we can solve it or not, that is important. So z minus 1 is this stuff. That is there. Z minus 1 is this stuff.
We cannot neglect anything.
Let's see. So phi will be, or ln phi will be just integration of this.
0 to P Z
So
minus 1
first
by
part
P
is
dt.
just PBRT. It will give PBRT. Nothing is there. And the second part is A P P will not be there. Okay. This RT square. RT square dp. So this part you have to solve, I think. Hmm.
How to solve it?
Again, you have to insert the Andrews equation, I think. Or in general, if you consider that this V m by b by vm square is independent of pressure, then it's okay. You can do it. Okay, but in general, what you have to do, you can try it. I have also do it because it's not. I thought it's trivial, but it's not actually. Okay,
Okay, I will
please
try.
do it. Yes, you will try, and next day I'll solve it. And also, there is another question that also you can solve. It is easy
Okay.
if you consider this as just RT, right? If you consider this as just
Yes.
RT, then it is easy. That is considered in book, but I don't want to consider that. Okay.
Okay.
Okay. So let me stop here today. And in next class, I will solve it and also one more question. Then, what is my plan? Then I'll discuss some miscellaneous question because in this week already the question answer is discussed. From electrochemistry, I will discuss some question. And then see in last class we will discuss that that Joule Thomson coefficient and the other stuff.
Okay.
Okay, so it's okay. So it's already 6:03. Okay, so let me stop here today. We'll again meet next week. Okay, at 4 p.m.
Okay.
Okay.
Thank you.